So now let us continue with block diagrams. So this is one reason why the Laplace transform and the transfer function excuse me, is the most useful way to look at these linear time invariant systems is as follows. So let us say I have something and its transfer function is g1 of s. Okay, so here I have in the Laplace domain I have u and I have an output. We will call it y1 of s. This continues. I feed that into another thing whose transfer function is g2 of s. Okay, very good. And then I get an output which is y2 of s. Okay, well, if I think of this whole thing as one plant g, what is the transfer function of g? Well, y1 is equal to u g1, y2 is equal to y1 g2 is equal to u g1 g2 is equal to g1 g2 u, because it is all algebra. And so g equals g1 g2 is net effective transfer function. Okay, mathematically, pay attention, mathematically g1 g2 equals g2 g1. Physically, maybe impossible. So mathematically I may prefer to think of it as g1 g2. Physical interpretation may be g2 g1. We won't care. Physically both may not be possible. So for example, I may have a big amplifier. This is such a big amplifier that I can drive huge speakers whose sound will be heard all over a stadium. And then I may have some little circuit with 2 op amps and some things like this. Now I can't take the output of the amplifier, drive the op amp and use the op amp to drive the speaker. That's not possible. Not possible. I may take this one here, put this one here and then drive the speaker, and that's perfectly possible. But in my analysis, g1 g2 is equal to g2 g1. So if you are a control engineer, you must remember which is the physical world with possibly big physical variables, pressures, large currents, things like that, and which is the signal processing world where everything is maybe plus minus 10 volts, plus minus 10 milliamperes. Within that you are arranging it so that you are working with the signals properly. Okay, so you have to remember that in the Laplace domain we can rearrange these blocks. In the physical world there are restrictions. There will be a part of your control system or your controlled system which will have small signals, little currents, little voltages. You have to remember that as an engineer. You cannot cross those lines or that sequence, but mathematically the sequence is clear. Okay, the second thing to remember is, or the second thing to learn is that we use this symbol quite often, right? And we will show something like this, maybe plus, minus, okay, and something comes in, u, and this is the output. Let this be y for the moment. Okay, so this, let me erase that to indicate I'm still talking in Laplace domain, I mean capital U. Okay, all right, what I mean is when something comes in here, let us say this is z, then y is equal to u minus z. It is just simple subtraction over here. Okay, so you can see, you know that this is possible in principle, there's no difficulty. Okay, by now we have some pieces needed for our control system. So here is the plant. This is the thing whose behavior we want to control. This is y of s, the thing that we want to behave in a certain way. Ideally we want y to be equal to u or something like this, but in any case we will see. Now here is u, our input to the system, right? Now suppose you are controlling the temperature of some air conditioning plant. In that case your actual desired input may be 17 degrees centigrade. So is it a number, is it a current, is it a voltage? You have to figure that out. But finally in the language of the control systems, or in the implementation at the control level, you will have reduced it to some voltage or signal of that nature, and then that is the u that we are talking about. Okay, now usually you may put some op-amp based card over here. Let's call it we can call it a compensator. Let me call it C1, compensator 1. Okay, C1. Maybe I'll have another amplifier which will multiply it by some constant gain k, then out here. But I will have feedback, so I will measure this and I may put it through some other compensator. This is just a measurement now. This is the physical variable, maybe 1 megapascal. This is just a some voltage from a pressure probe, right? But we are treating them mathematically the same. I hope you understand that. C2 of S, this is compensator 2. Okay, so this is our control system. Let me put a box around it. We will spend quite a bit of time in this course trying to understand what this means. Let us first remember that from here to the application world, this is the physical world. Physical world, big forces, etc. Right? And this part here is electronics. Now of course people may get annoyed and they may say electronics is also part of the physical world. I agree, but what I am saying is this is millivolts, milliamperes, they are in our control. This may be megapascal, you may be shaking a gigantic bridge, or it may be temperature, it may be Kelvin, it may be stress, strain, fluid velocity, so many others. So you cannot really just sort of take this one and put it between the amplifier and the plant or something like that, is what I'm trying to say. Okay, so there are these two worlds that interact when we design a control system. And now finally I want to know what is y as a result of u, okay, in terms of Laplace transforms. So it is easy enough. Y is here, this is y, that means this is C2y, that means this is u minus c2y, then u minus c2y times c1 times k times g is equal to y. Okay, that's what it is, because each just this is how Laplace transforms work, right? So this is why you will see, if you were trying to think of it in terms of differential equations, reaching this level of simple understanding would be extremely difficult. But now you are able to see this transparently. Okay, what is the consequence of this? The consequence is I want to isolate y, so I will take this and take it over to the other side. So I will have u into c1 kg is equal to 1 plus c1 c2 kg y, but then I will write it like this. I will write it as y equals k c1 g over 1 plus k c1 c2 g times y, sorry, u. Okay, so I hope it is clear to you by now that this is the effective transfer function of that control system. I will write here CLTF, closed loop transfer function. Okay, all right. Why is it closed loop? It's closed loop because this is the loop. This is the loop here, and it is closed here. Okay, so that's the closed loop transfer function, and the behavior of the CLTF, this impulse response function is what is going to determine how the system will behave when it starts from zero initial conditions and is given some input. It is really important for you to note a very simple thing over here. What is in the numerator? In the numerator you have the product CKG, right? 1, 2, 3. In the numerator you have the product of the things in the forward path, not C1. Okay, so you have the product of the things in the forward path. In the denominator you have 1 plus the product of all the things in the loop. Okay, so if you remember this, then just by inspection, without writing this equation, you will always be able to write it. Okay, you will also notice that I have moved this k to this side. Okay, physically the k may appear after c, but mathematically I can put the k before c. Putting the k before c is sort of interesting because when I am operating the system, I have made this card with op amps, right? So that I can't change. But over here the amplifier gain will be something that I can usually change. The gain is something that we can change when we operate, and so we like to leave it as a free parameter and try to understand its effect on the dynamics of the system or the performance of the system. Okay, so here we are, closed loop or open loop. We are down to y of s is equal to h of s times u of s. Okay, this is a rational function of s, We call it the transfer function of the system. Okay, the transfer function of the system, whether closed loop or open loop. This transfer function can be thought of, if we like, as the Laplace transform of the response of the linear time invariant system when it starts from zero initial conditions and is given an impulsive input, a Dirac delta input. Okay, there are other interpretations, but this is something to work with. If it is a lightly damped structure which vibrates a lot, then this is a perfectly good way to think about it. If it is some big piece of rubber or has long delays and some slowly changing temperature, then it is not a very good way to think about it. But in any case, we have gone through this derivation in other ways and you are, I hope, comfortable with it. So our next question is, given h of s, what is the response like or system behavior like? Okay, and 2, given a plant g of s, how to choose C1, C2, K to obtain good behavior. Okay, so I hope you understand that first we must know this. Once we know this, then we can see the role of these things on that. Okay, and in this way we have come to a reasonably clear statement of the goal of this portion of the control systems class. Okay, so out of the big world of systems, multiple input, multiple output, non-linear, time varying, non-smooth, out of all those we have simplified, abstracted, linear, time invariant. We have dropped the role of initial conditions. We have used Laplace transforms, used the algebra of block diagrams. We have indicated that at least some simple compensators C1 and C2 can be made in principle with op-amps. We believe in the existence of amplifiers. We've not sort of thought about them much, but we know we can use them, so we are referring to some gain. We have got the idea of the basic closed loop controller design, and then we have got the closed loop transfer function. And now with these background ideas in our head, in subsequent lectures we will think about these two questions. Given h of s, what is the response like, where h of s is that over here you see, and given a plant g of s, how do we try to obtain a good h of s, where our tools are compensators C1 or C2 and an amplifier gain K. C1 for compensator in the forward path, C2 for compensator in the feedback loop. That's all for now.